Okay, so as I mentioned last time, we still have quite a bit of material to get through, so we'll put exam 4 on Monday. So we'll finish SN2 today and start SN1, and then on Monday we'll finish SN1, and then you'll have your module 4 exam then. Any questions before we get started? So we were introducing the different elemental nucleophiles for SN2, and we started with carbon, and these are basically reagents you can buy. So potassium cyanide, that introduces an sp hybridized carbon into the molecule, forming a nitrile. And as I mentioned, please review the spectroscopic signatures for the different functional groups as they're introduced. Sodium propionylide, really this could be any terminal alkyne that's a carbon anion can be used. Again, that's an sp2 hybridized carbon. And when it undergoes SN2, you're now forming an internal alkyne. So internal just means the triple bonds inside the carbon backbone. Nitrogen nucleophiles, ammonia in theory is, you can use it, but it gives you a lot of products. And really the reason it's not a good nucleophile is it has those basically acidic hydrogens to it. What happens in the SN2 reaction with ammonia, so there's the backside displacement. Those hydrogens can be deprotonated because you're in the presence of a base, ammonia, so it can do a proton transfer. And that would lead you to methylamine. And so methylamine still has a lone pair, and that can get further alkylated through another equivalent of, say, the methyl bromide. So you can go from a primary to a secondary to a tertiary and ultimately to a salt. And depending on the concentrations of things, you probably end up with a mixture of those. And then one of the difficult things in organic chemistry is separating out the components of a mixture. In lab, have you done distillation? So if you're taking a pure liquid and distilling it, you're really just finding the boiling point. But if you have a mixture of liquids, that's a method of separating them based on the boiling point. So liquids are kind of easy to separate if the boiling points are reasonably far apart. When you get into things that are solids are not so easy to separate. A classical method of purifying solid mixtures is through crystallization or recrystallization. But in general, the most common technique is chromatography. So have you done thin layer chromatography yet? So you might have done it in Gen Chem or maybe even high school. You take like a paper filter, you put like a Sharpie dot in the middle, and then you have solvent, and like a black Sharpie will separate out into different colors. So that's an example of chromatography. So our goal in organic chemistry is to design a reaction that produces one thing in 100% yield. If you end up with mixtures, then you have to separate them, and that's just time and money component that's added. So what is the alternative to using ammonia to introduce nitrogen into a molecule? So here are two examples of nitrogen-containing reagents. So the nitrogen's nucleophilic, but what you'll notice is the nitrogen is not bonded to any more hydrogens. So that's really limiting the nitrogen atom to having one nucleophilic lone pair. So it can only undergo one SN2 reaction. The first reagent is called sodium azide. So again, that's an inorganic salt, Na+, and then N3-. What does N3- look like when we expand into like a Lewis dot structure? Is that right? 5. 1, 2, 3, 4. I think that's right. I think it needs 3. So what that's doing is putting an azide in. So the same thing, backside attack, and now we have an azide. So because that has a triple bond, in the IR, you'll see a signal from 24 to 2200. Additionally, because there's an odd number of nitrogens, the parent mass will be odd. So you can use azides for many reactions, but really the nitrogen atom has basically N2 bonded to it, and it can be reduced to an amine. So azides can undergo reductions to amines. That's chemistry that's probably more for 256 when we get into more specific functional group reactions. But that's how you get N into a molecule. The other reagent is called potassium thialimide. And that's a salt as well, so potassium's plus, the N is minus. So that bond you can think of as an amide. That bond you can think of as an amide. But when the nitrogen has 2 of those, they combine into one functional group called an imide. So that's where that name comes from, thialimide. A nitrogen with 2 amides. So that allows you to install the nitrogen, and that makes a thialimide, so that would be N-methylthialimide. And again, it's when we look at the nitrogen atom, these bonds I'm cleaving in red, you can remove those to form methylamine. That's called a deprotection. And we're not going to go into those conditions or that mechanism now, but what you need to know is that potassium thialimide is a reagent to get the nitrogen into the molecule. Any questions? So again, we're moving across the periodic table. We're now at oxygen. the conjugate base of an alcohol can act as a nucleophile. So sodium methoxide is derived from methanol, in which we've added sodium metal. So sodium metal is a silvery looking solid. You can put it into a flask containing methanol. You'll see some fizzing happening, and eventually that solid sodium metal will dissolve. And you're losing hydrogen gas as the bubbles that fizz away. So that generates now sodium methoxide. In the context of an SN2 reaction, this is acting as a nucleophile. So keep in mind again, diagnosing the conditions that are present, even though that sodium methoxide is the conjugate base of methanol, it's acting as a nucleophile. So when that gets introduced, that forms an ether, and this has a name called the Williamson ether synthesis. We could also use the conjugate base of carboxylic acids. So potassium ethanoate. So how would we make that? So we could start with ethanoic acid, treat that with sodium hydroxide, or potassium hydroxide. Any hydroxide, again, the metal here, you can use lithium, sodium, potassium, whatever. The conditions that would make you choose one over the other can partially be determined on the salt that's formed. So if you harken back to your Gen Chem labs, you probably did something related to the solubility product constant of inorganic solids. So you could determine, hey, potassium bromide is not very soluble, so it's going to crash out once it's formed, and that helps drive the reaction forward. But any lithium, sodium, or potassium hydroxide you can use to generate that carboxylate. The mechanism's the same, it's SN2. And in this case, you end up with an ester. So we have that ester carbonyl between 18 to 1700 reciprocal centimeters. Any questions? So here's a series of 4 different electrophiles. And we want to treat with potassium cyanide in acetone. So we can diagnose this as SN2 because we have a strong nucleophile. It's present in the form of a salt, so a metal cation, a nucleophilic anion, a polar aprotic solvent. Now we want to look at the choices A, B, C, and D and determine which one reacts the fastest. So before we get to that, which one can we eliminate? Which one's not going to react? Which one is unlike the others? C. the carbon bearing the leaving group is sp2 hybridized. So for SN2 reactions, that carbon has to be sp3. So A, B, and D, they're all sp3 hybridized carbons, and then we have to rank them somehow. So what's the classification of response A? So secondary, and then B is primary, and D is primary. So from that, we can eliminate A, because we know primary is going to react faster than secondary. And then what's the difference between B and D? So this carbon here, that's the allylic carbon. And we saw from the radical substitution chapter that allylic carbons tend to be the most reactive. So that sp3 hybridized carbon bonded to the alkene imparts a special reactivity. So D is going to be the correct response here. And you can think of this as like a race. If you put all 4 of those compounds in a flask, dissolved them in acetone, and then added potassium cyanide, D would be the one that starts forming the product first. Questions? Yeah.
How are we going to separate the ether? How are we going to distinguish the ether? Right? You mentioned that we can separate the ester by looking at the ion. What about ether?
So of all the functional groups, ethers are probably the most difficult to figure out through spectroscopic methods. They don't have any unsaturation in them. They don't have a carbonyl. The oxygen really doesn't influence the mass spec too much to give you like a unique signature. Probably the best thing you can look for say in the 1H NMR. So we have the oxygen bonded to that carbon. These hydrogens bonded to that carbon. You'll probably see a chemical shift of those signals between like 3 and 4. So that's telling you that the carbon atom is bonded to a heteroatom. It confirms some things, but it's not giving you a lot of confidence. The C13 as well, that carbon bonded to the oxygens, those might be, say, 30 ppm to 60 ppm. So really what you have to do is you're trying to prove it's an ether, but you can also disprove other functional groups. For example, nitrogen by going back to the mass spec if there's an odd mass for an odd number of nitrogens. So again, it's using positive evidence that it's there, but also the lack of evidence to reject other functional groups. So here's the kind of similar question, just phrased in a different way. You'll see this sort of format on your final exam where you're asked to rank things. And it says, which is the order from fastest to slowest for the rates of SN2 reactions of these alkyl halides with sodium methoxide and DMSO. So which one reacts the fastest? So that's the fastest. So in terms of the responses, that has to be the first number. So I've rigged the responses here. So the answer ends up being B. So that's primary allylic. Choice 3 there is secondary. And the first choice there is tertiary. And really we're just putting the class into the rank. So SN2 rate was methyl, was greater than primary, greater than secondary, and essentially tertiaries are unreactive in SN2. So now you're asked to look at an electrophile. So I would say that is a secondary iodide, and you want to substitute it for an azide. So what would be the most appropriate nucleophile to do that? Sodium azide, so D. Again, that's a strong nucleophile because it's of the form sodium. And then N3 minus. We can eliminate A just through logic. There's no N3 in there at all, right? We can eliminate C for the same reason. And then what about B? Why is B not a good choice? So there's not a metal. So what that's telling you is the iodine is covalently bonded to the N3. So even though both of them have N3, sodium azide, that's a salt, an ionic bond. Iodoazide, that's a covalent bond. So that pair of electrons is shared. And that if it's shared through a covalent bond, it's less able to be nucleophilic. So here we're going to talk a little bit about strategies with alkyne nucleophiles. So in the synthesis of alkynes, there can be two means of synthesizing any alkyne. So we're designing a plan. In either way, the electrophile, so that's the molecule bearing the leaving group. So in either way, there is an electrophile, and the nucleophile is an sp hybridized carbanion. Given those facts, what reagents could accomplish the synthesis of 2-hexyne? So the 2, again, is telling you the start of the triple bond on that chain. So what do you think? Huh? So A is the correct response. So 2-hexyne, that tells us we need 6 total carbons. If we look at choice B, and we count. 1, 2, 3, 4, 5. That's not enough carbons. We can do the same for C. 1, 2, 3, 4, 5, 6, 7. It's too many. What's wrong with choice D? That seems to have 6 carbons. So there's no leaving group. So that's 2-hexyne. And choice A is one way of making it. So really what we're thinking about, we want to make 2-hexyne. So we're breaking that bond. And then we're making this side the nucleophile, that side the electrophile. So the nucleophile has to have a lone pair, the electrophile has to have the leaving group. So that was one way, that's the blueprint for choice A. Let me ask this question. The other way that you could make 2-hexyne, what would the name of an electrophile be for that? Let me ask it a different way. How many carbon atoms would the electrophile have? What'd you say? So what you're doing is you're isolating the triple bond. From the triple bond, you're then breaking the carbon bond next to it. So in that first way, that sp hybridized carbon, sp3, we're breaking that, that's getting a leaving group. So that forms the propyl bromide. In the other way to design this, we're going to break that bond. That's still going to be the nucleophilic carbon here. That's going to be the electrophile, so 1 carbon, and then we stick a leaving group on there. So the other way of doing it, would have a 5-carbon nucleophile and then a 1-carbon electrophile. As long as we stick a reasonable leaving group on there, we can use, iodo, chloro, bromo, whatever. So anytime you see an internal alkyne, there's 2 ways of disconnecting it, 2 routes. So we make those alkyne nucleophiles using acid-base chemistry that we learned in the prior module. So that's a terminal alkyne. Terminal means you have that H. we know that's an acidic hydrogen. So the pKa is about 25. We can treat that with sodium hydride. That will deprotonate that CH. That generates the nucleophile. We then trap it with the electrophile. So part of, not only learning the reactions and the conditions, but if you're given a target, how can you look at the functional groups in that target molecule and apply the reactions that you've learned? So in that sense, you have a destination, but you're working backwards to a starting point. Any questions before we move on to the next factor of SN2? So that was just a very small library of different nucleophiles: nitrogen, oxygen, carbon. The next issue with the SN2 mechanism is stereochemistry. So we talked about stereochemistry in our prior module when we were generating stereogenic carbons. Those are carbons that have 4 unique different substituents. So for these, we're going to consider a secondary halide. So we have 2-bromobutane. That's a secondary bromide. And when we look at the carbon atom, so that carbon, it has a bromine, a methyl group, an ethyl group, and then a hydrogen. So it's 4 unique substituents, therefore it's a stereogenic carbon. The wedge is showing you that the bromine is coming out towards you. And we already stated that in the SN2 mechanism, the nucleophile has to attack at a trajectory that's completely opposite to the leaving group. So let me put in, I'll do it in green. I'm going to put that hydrogen in green. Hopefully you can see green up there. See how the hydrogen's back in the starting material? When the azide displaces that bromide, that hydrogen gets moved forward. That's called inversion. So again, the main thing is based on that lone pair has to come in at 180 degrees from the leaving group due to the location of that sigma star orbital. So let's dig a little bit into the consequences of that. So a consequence of this backside attack of the nucleophile on a stereogenic center is there is complete inversion of the stereogenic center. So that wedge that's coming out towards you, the reaction happens, the dash is going behind the board. So it says, what is the nature of the transition state? So we can look at that secondary carbon. If we count all the bonds to it, they're all sigma bonds, right? So 4 sigma bonds, that's telling us that that's sp3. We do the same for the product, that's sp3. So what's the nature of the transition state? Why does it invert? I'm thinking about how I want to draw this so it's not unclear. I want to draw that the carbon-bromine bond in the plane of the board. And then I'm going to put the other substituents in there with some stereochemistry. So basically what I'm going to do is kind of rotate the carbon-bromine bond so that's in the plane, and I'm going to sort of move it in a specific way. So we want carbon-bromine in the plane. I think that's the right stereochemistry. So there's that sigma star orbital. That's where the electrons from the nucleophile have to go into. And it's completely opposite to the carbon-bromine bond. So those electrons are going to go in there. The carbon-bromine bond is going to break. Now the transition state is that very short-lived intermediate where you have a carbon-nitrogen bond forming and then a carbon-bromine bond breaking. So the carbon has to do something to accommodate that because now it's 5 total substituents. So in the square brackets here, that just means the transition state. The carbon has to rehybridize from sp3 to sp2 because that allows it then to have a p orbital that can accommodate sort of these partial bonds. So making and breaking at the same time so that it's a synchronous process. So our carbon now is sp2, and that was the p orbital. we already learned that sp2 hybridized carbons aren't chiral. So those three substituents, methyl, ethyl, and H, see how they were all on sort of the left side of the molecule here? In the transition state, they're all in a plane because that sp2 hybridized carbon is trigonal planar. So they go from one side into a plane, and as the nucleophile attacks, those substituents are then inverted to the other side. So that's the inversion. And the transition state is the highest energy on the reaction coordinate. Questions? So it says in terms of RRS, you still must determine the priorities of the products. And the caveat here, which I'll highlight in red, do not assume that an R stereogenic center becomes an S or vice versa. You still have to determine it. So let's put that to practice. What are we starting with and what are we ending up with? Is that right? So just let me state that again so I'm clear that you're clear. Remember, a stereogenic center, you're going to assign RRS to it based on the SIP priority rules. And SN2 is going to invert that center. So it would be natural of you to think that an R must become an S because there's an inversion. That's correct probably 95% of the time. When it's not correct is when you're using an element in the nucleophile that has like a different or lower priority than what you're starting with. So sometimes an R stereocenter can remain R. So just be clear that the wedge to dash inversion always happens. The SIP nomenclature you have to validate. Don't necessarily assume that that's flipping from one to the other. Let's just review this here in terms of assigning R and S. So for the 2-bromobutane, bromine gets priority 1. The hydrogen is going back, that's priority 4. Of the 2 carbons, the one in the longer chain is the second priority, and then the shorter one is the third. So our steering wheel here is going clockwise, so that gives us the R. That would eliminate A and C. When we did the inversion with nitrogen, N is still taking priority. The hydrogen's now in front. So 1 and 4 of the 2 carbons, those stay the same. Notice that that is still going clockwise, but the 4 group is in front of you. So that has to change from R to S. So we would end up with D is the correct answer. Questions? So as a nucleophile attacks the antibonding sigma orbital of a carbon-leaving group bond, so that's this, that's the sigma bond. The antibonding orbital is right behind it, so sigma star. The carbon atom undergoes a rehybridization to sp2 in the transition state. A consequence of this is the inversion of that carbon. This is witnessed when the carbon is stereogenic. What is the product of the following reaction? So again, to highlight the inversion, your carbon-leaving group bond, that's in the plane of the board. H, this long chain in methyl, see how they're all over to the left? The sodium hydroxide is attacking this way. These three groups are going to flip over to the other side. So how can I reasonably do that fast? The OH has to be in the plane opposite to the carbon-bromine bond. There's the nucleophile, there's the carbon. The H is still in the plane, but we're flipping it over to the other side. The methyl group is still pointed out, but now it's on the other side. And then the rest of the chain, it's still going back. So I'm going to say left and then right. And, you know, that's assuming that the carbon-leaving group bond is in the plane, and then you're adding the nucleophile in the plane. So when we do that, what is the name of the product? I heard a B. I don't think so. Any challengers? Anybody want to arm wrestle over it? Not that confident. Huh? So it's got to be A or B. So there's an alcohol in it, so it can't be the bromo anymore. If we count the carbon chain, the alcohol has to be at position 2, so it can't be D. So let's assign priority to these. We have a carbon bearing an O, 2 C's, and an H. The oxygen's going to get priority 1. The hydrogen's priority 4. Then we have 2 carbons. The carbon with the longest chain gets 2. The shorter chain gets 3. So the way that I look at this, I imagine putting my eyeball opposite that CH bond. So my eye is down here, and I'm looking that way. So I can sort of do that in my head, and then when I do that, the 1 going to the 2, that's starting counterclockwise, so that has to be S. Or alternatively, your model kit for your lab, all you really have to do is just make 1 carbon and take those little balls, take 4 different colored balls, and you can do that. Just assign them different things and then hold it in the way that the rules say. So true or false, the measured specific rotation, either plus or minus, is dependent upon the CIP R or S designation. So that's false. The CIP-RS comes from the priorities you assign according to the atomic numbers of the elements, the sign of the specific rotation is measured. You have to put the sample in an instrument, it's spitting out the result. So unless you're genetically built different than every other human being on Earth, your eyes cannot determine that. It has to be measured. And so there's no connection between what we as humans assign R and S and what the instrument is spitting out as plus or minus. So which of the following best describes the properties required for a successful SN2 reaction? What's the nature of the kinetics, the solvent, and the nucleophile strength? You said D. Close. There's 2 out of 3 right. So C. So we need an aprotic solvent. So that SN2, the 2 stands for bimolecular. The solvent has to be polar aprotic. Again, that helps not only dissolve the starting materials, but also sequester the metal cation, exposing the lone pair for the nucleophile. And nucleophile strength is strong because you're dealing with typically a metal cation and then the nucleophilic anion. If the free energy of activation for an SN2 reaction is positive, but overall the free energy change is negative, what term describes the thermodynamics of the process? So that's the first part. The free energy change is positive. But overall, it's negative. So that the energy of activation is endothermic, but overall, since we're dealing with the delta G term, it's exergonic. So in the reaction coordinate for the SN2 is fairly straightforward to interpret. As we'll see in a couple minutes here, when we get to SN1, the terrain of that curve is a lot bumpier. So to review the SN2 mechanism, here's the bunch of promoting factors. So I'm highlighting that in green. The different factors, there's the SN2 mechanism. The electrophile, again, keep in mind what allylic and benzylic mean. So methyl is greater than primary, greater than secondary, and tertiaries do not react. The leaving group, typically a halogen of that order in terms of the rate. Iodine's greater than bromine, greater than chlorine. or if we have those activated alcohols, so those sulfonate esters, we want a strong nucleophile. So M plus nucleophile minus. That relates to nucleophilic charge. You want that nucleophile to be anionic and not neutral. Solvent type, polar, aprotic. So aprotic means without OH or NH bonds. Those type of solvents, again, these are the abbreviations, so you should go back and look at what the structures are so you understand how they're polar, how they're aprotic. Kinetic order, or kinetics, that's the 2 of SN2, so second order. The rate equation depends on the concentration of both the nucleophile and the electrophile. Stereochemistry, we just saw there's complete inversion. And then I have this last thing, rearrangements. It says not possible. So we have to go through the SN1 mechanism. Why? Because this right here, tertiary groups. So tertiary substrates still react, they just do it through this. So what do you think the 1 means in terms of the mechanism? So unimolecular. So it's a unimolecular mechanism. The kinetics only depend on the concentration of the electrophile. In the last row, if this says not possible for SN2, what do you think it should say here? Possible. So this is where you're at the buffet, right? You're hungry, you want to eat something, and we're not piling a lot of food on the plate. So as with any good parent, you have to finish all your food. So you're going to get pretty full here. Overall, if you identify the carbon bearing the leaving group, that is where the substitution is happening. Now, based on the classification of that, it either goes SN2 or SN1. For SN1, there's these other things now we have to consider in terms of the promoting factor. And so it's going to go through a different intermediate in the mechanism. So thus far, our primary decision point about substitution was classifying the nature of the leaving group. The SN2 trend said methyl reacts faster than primary and secondary, and tertiaries don't react. However, it does not mean that tertiary substrates fail to undergo substitution. They do. It's just this alternative mechanism now. So tertiary substrates undergo SN1, which means they proceed through a different transition state. They have intermediates, but ultimately they're going to be substituted. The other thing to diagnose in the reaction conditions is that the solvents and the nucleophiles are therefore different. So you might have even run this reaction already in lab. You tell me. Did you take like tert-butyl chloride or tert-butyl alcohol or something at some point? Like tert-butyl chloride with silver chloride and water? Doesn't sound familiar? Okay. So as we go through this, maybe it'll jog your memory. How many more labs do you have left? Just one, maybe it's the last one, who knows? So the SN1 mechanism is referred to as another term called solvolysis. So we know what the word hydrolysis means. So lysis means cleavage. Hydrolysis is cleavage by water. So solvolysis is cleavage by solvent. Questions? So the rate for SN1 is opposite SN2. Tertiary reacts faster than secondary. Primaries will not undergo this mechanism, asterisk, unless they're allylic or benzylic. So that would be allylic. So primary allylic. That would be primary benzylic. So in the reaction in the middle of the slide, if I expand that substrate out, that's a tertiary bromide. So that's called tert-butyl bromide. If we take tert-butyl bromide, put it in ethanol, and typically we're adding some heat, what you see is a substitution. So that bromine I'm highlighting in red, that gets substituted for O-ethyl. Where does the O-ethyl come from? It comes from the solvent. So what do you notice in here? The solvent and the nucleophile are the same thing. So when you look at a reaction and you don't see that other thing, that separate nucleophile, it's a good indication it's an SN1 reaction. So as I said, the mechanism is different because now it proceeds through an intermediate. An intermediate is a well that exists along the reaction pathway before you get to the product. The name of this intermediate is called a carbocation. We know the leaving group has to leave, right? So in the SN1 mechanism, it's not immediately displaced by the nucleophile. It first ionizes. When we look at that carbon-bromine bond, from electronegativity, we can do that. Bromine's more electronegative than carbon. So what happens first is that CBr bond ionizes. So the bond cleaves. So there's two ions, a carbocation and a bromide anion. The charges balance. You have 1 plus, 1 minus. You sum that together, you get 0. So the ionization event is the rate limiting step in SN1. So that means when you're looking at the reaction coordinate, that's the highest energy that you have to overcome to get towards the products. So carbocations are typically shorthanded as like R+, that tells you it's a carbocation. So as I said, that C leaving group, that bond ionizes. Notice that arrow? It's a full arrowhead, so both electrons in the sigma bond are going to be owned by bromine. So when that happens, the carbon has to bear a positive charge. It becomes the carbocation. And carbocations are sp2 hybridized. So the plus charge resides in the p orbital. Remember, a p orbital is dumbbell shaped. So the plus charge it's in both lobes on either face. And I'm just showing one. So I'm showing one here where the nucleophile is then attacking, we'll say, the left lobe. It can also attack the right lobe equally, and it will. So once that attacks, you've now formed an oxygen that's plus charged. This is called an oxonium ion. And you should be a little bit familiar with that. When you protonate water, that forms hydronium. Now we just have some carbon substituents, so it's called oxonium. And then the last step is an acid-base reaction. That allows us to form the neutral product. And in this case, because the solvent was an alcohol, we end up with an ether. For the most part, what can I tell you about SN1? Because the solvent is the solvent and the nucleophile, you're really only limited to forming ethers and esters. So whereas with SN2, you can kind of introduce any functional group, SN1, it's ethers or esters. So this is what the reaction coordinate for SN1 looks like. We have three factors we want to describe. How many transition states are there? How many intermediates? And then what is the thermodynamics for the reaction overall? How many transition states do you see? So that would eliminate A and D. So the transition state, again, it's the crest or the apex, top of the curves, so there's three. Intermediates are wells. How many of those are there? So two. And then relative to this horizontal line, where is the product ending up, above it or below it? So below it, so that has to be exergonic. So then our answer would be B. So here it is now with a lot more stuff. What is happening at each step in terms of a transition state or an intermediate. From your starting material, the tertiary bromide, notice that arriving at that first transition state, that's the highest you have to climb. So that's the rate limiting step. We have to get over that big hump first. So it's endergonic, we have to put energy in. It's a transition state because that bond is partially ionized. When it gets fully ionized, now it's in the well, that's an intermediate. So the carbocation has a longer lifetime. The next transition state we have to get over is when the solvent / nucleophile is attacking, so we have partial bond formation. Then we get down into another well of the oxonium ion, another transition state proceeding through the acid-base reaction, and then we're ending up at the neutral product. So overall, from where we started, that horizontal line, to where we end up, we're lower, so that's exergonic. So let's look at this last bullet point here. See how it says racemization? So what exactly does that mean? Imagine these three groups here, these three methyl groups. If they were all different, that carbon would be stereogenic. We could assign it R or S. When the leaving group ionizes and we get to the carbocation, those three groups are all in a plane. The positive charge resides in either lobe of the p orbital. The nucleophile can attack to the right or to the left equally. So when it does that, a consequence of it, again, imagine these are three different substituents. You end up with both R and S in the product equally. So that's what is meant by racemization. So in an SN1 reaction, the weak nucleophile attacks which orbital? So that's B, the p orbital. Again, that's where the plus charge resides. The p orbital is commonly visualized as a dumbbell. So again, the two lobes on sort of either face of the molecule. So our last slide here as we wrap up. In an SN1 reaction, the blank ionizes to a blank with blank hybridization, resulting in a complete blank of stereogenic center. So in the SN1 reaction, because it's unimolecular, the electrophile ionizes, so that gets rid of C, to a carbocation. That gets rid of B. With sp2 hybridization, so D, resulting in complete racemization of the stereocenter. So again, that's a verbal description of the mechanism the prior slide had shown, the arrow pushing in the structures of those intermediates. So we'll continue on Monday where we look at what is the stuff in the flask, so the solvents. Now again, because it's SN1, the solvents are opposite, so they're polar protic. Why do they need to be protic? We'll discuss that.